Hi, it's Dr. Khan with Chapter 5, Sections 5.1 and 5.2. The chapter starts off talking about earthquakes and the forces and mechanisms that generate most of our earthquakes. We'll also look at the different types of seismic waves and properties of those seismic waves. Understanding those will help us in the next section, 5.3, talking about how we locate the epicenter of an earthquake. So, an earthquake is the shaking of the ground caused by a rapid release of energy along areas called faults. As a result, there are seismic waves, which are waves of energy that travel through the earth and along the surface. There are two words here that mean the same thing for the location inside the earth where the slipping actually begins. It's either called a hypocenter or a focus. This is again in the ground where the slippage of the rocks begin. If we draw a line straight up from that location, the point where it meets the surface of the earth is called the epicenter. Here we have a good figure in the book that shows where the hypocenter is, or the focus. This is where the slipping originates from, but it slips along this entire fault. And again, if we draw a line straight up from that focus, we get the epicenter. So that's a point that we would plot on a map of where the earthquake took place or originated from. Seismic waves are sent out in all directions. We'll see that there are three main different types of waves that we'll address in this chapter. So the plate tectonics theory gives us a basis of understanding why earthquakes happen. We know that plates are moving and exerting a force against each other. So there's pressure that's built up. That pressure builds until it overcomes the ability of the rock unit to withstand those forces. There's a slippage along that fault, a sudden slip or release of energy, and those rocks then spring back essentially into place or into their new location, and that's called elastic rebound. So they're returning back to their original shape. This is actually something that's well demonstrated in the SMART figure for elastic rebound, using a stick as an example of how it breaks. I do recommend at this point you pause this video and take a look at that SMART figure for elastic rebound. Earthquakes are often preceded by smaller foreshocks and then followed by aftershocks. So foreshocks are smaller magnitude that come before major earthquakes, and aftershocks are lesser magnitude earthquakes that can occur days, weeks, or even months or years after a major earthquake. This is kind of the settling into place of the rock units after they've slipped. So plate boundaries can be associated with different types of earthquakes, and our most, largest magnitude types of earthquakes are typically along these convergent boundaries where two plates are coming together. I'm specifically thinking about those subduction zones where that denser oceanic plate is subducted underneath either an ocean plate or under a continent. And it doesn't move smoothly, right, like my hands are suggesting, right? And instead, there's a lot of buildup of stress and strain over time with those rock units pushing together, and you get this slipping of one plate under another. Transform boundaries that are sliding past each other without destroying or creating crust, those can produce earthquakes along different portions of that fault. So the whole thing doesn't have to slip at one time of that whole boundary. So you have this pushing up against each other in opposite directions and a slippage that occurs. It can also generate pretty large earthquakes. Divergent plate boundaries, on the other hand, think about your mid-Atlantic ridge moving apart. Those do also produce earthquakes, but they're smaller in magnitude. These big ones with the subduction zone are called megathrust faults. So these are the sites of the largest earthquakes that have been recorded on the surface of the earth, with one plate subducting under an overriding plate. Three terms that are similar to each other in the study of seismology, chapter 5.2. When we're looking at earthquake waves, we have ways to measure and record these using instruments or tools. So seismology is the first word or term that just refers to the study of earthquake waves. A seismograph is actually the instrument that's recording the seismic waves, and then we have a record of those waves that's produced called a seismogram. The SMART figure does a great job of giving you an overview of how a seismograph works to produce a seismogram. So please pause this video and take a look at that SMART figure video. Three main types of seismic waves that you need to know about include two types of body waves and a type of surface wave. So body waves are waves that are seismic waves, in other words, waves of energy. These body waves are traveling through the body of the Earth. So they travel through the Earth. First is the primary wave or P wave, the type of wave that's generated from a push or pull compressional motion. And it's often helpful to think about these as a slinky, and using a slinky, pushing it compresses it, and then pulling it back out expands it. And that compression wave will travel along the length of the slinky. So we push and pull, and that compression wave is traveling from one end of the slinky to the next. The particles are moving back and forth. So they move up and then back into position. These are the fastest traveling of the seismic waves, and it's important to note that they can travel through solids, liquids, and gases. They're the fastest. Our secondary wave has a shaking motion. Kind of think of it like a snake or an S shape here. So here's the rope at rest, and the hand is going to move up and down, and that's going to send this wave down the length of the rope. The particles, instead of the compression wave moving horizontally, in this case, the particle motion will be up and down. So it goes up and then it comes back down. I think of this type of wave, the secondary wave, as kind of doing the wave at a sports event when everyone stands up, when the person next to them is standing up and waving. That's what's happening here. The particle's moving up and down in place, but that wave energy is moving perpendicular to the particle motion. Particle motion up and down, wave direction to the right. That's a perpendicular relationship there. And surface waves. Surface waves, like the name suggests, are waves that travel along the surface from the point of the fault slippage outward. It is a complex motion. There are several different types of waves that can be associated with surface waves. They're the slowest out of all the waves, but they're the most destructive because they are traveling along the surface where our built infrastructure is. If we take a look at a seismogram, take a look at the readout, what we would see in case of an earthquake here is first the primary wave arrives. We see this as the offset of this line here, and then the first S wave occurs. And then we start seeing the shaking from the surface waves, assuming that we're at least somewhat close enough to the location of the earthquake to feel those surface waves. It's interesting to note in the next section, we'll look at the arrival time of the first P wave compared to the arrival time of the first S wave. And that's going to be very helpful in terms of being able to figure out how far away this earthquake took place from where this recording station exists. So here it says the interval time of 5 minutes between the arrival of the first P wave and the arrival of the first S wave. 5 minutes in between those.